So far in the last lecture we have discussed the mechanism of the hydrate formation, and we discussed how the hydrate forms. We have discussed also what something called the hydrate formation curve. We will discuss the region where it is safe to operate, or where the region where it's not safe to operate. We have discussed what we call the hydrate formation temperature and hydrate formation pressure, and we saw how to obtain these data using graphical solution or using empirical formula based on the specific gravity of the gas that you are dealing with. And we have seen several mathematical formula where it's suitable, for example, to use it in sour gas, and which one is good, for example, for sweet gas. Now we're going to look at the hydrate prevention, but before we start with the hydrate prevention, we need to look at one point that we need to highlight from the previous lecture, where we calculated, or once we calculated the hydrate formation temperature, it's always to keep in mind that we need to stay in the safe side. So as a result, we add something called the design margin, where the design margin accept or recommend that once you calculated the hydrate temperature, for example, you add 3 to 5 degrees Celsius to keep it warmer than the calculated hydrate point. So let's assume that you have calculated that the hydrate will form, for example, at 17 degrees Celsius. So it's recommended always to say that to add 3 to 5 degrees Celsius to the margin to make the stream warmer, which means that you're gonna reduce the chance, or you're gonna operate more in the safe side. So if your, for example, calculated hydrate temperature is around 17, then it's good to say that, okay, or it's safe to say that we need to operate at around 20 degrees Celsius instead of 17, just to add these margin for design as well. Now, as we explained earlier, that the hydrate formation will cause a lot of operational problem, and one major problem is that it's going to cause blocking of the pipe, or it will block the flow in the pipe. And this will cause, for example, several issues. Operational issue will cause upset in the production, will cause upset in the flow of the gas, will cause a huge pressure drop in the pipeline that you are dealing with. So normally, when you have the scenario, or when the scenario is where you have, for example, temperature drop, which means that you have a condition, because you have to keep in mind that we said that the two optimum condition for the hydrate formation is two things: for high pressure and very low temperature. So normally, when you transport the gas from the gathering station, for example, to the on-field processing station, or to the on-field plant, for example, you might experience something called pressure or temperature drop, and this temperature drop will cause, or will contribute, or will provide a good condition for the hydrate to start forming. So the temperature drop can come from several things. It could be the GT effect at the wellhead, and we're gonna see what do you mean by the GT effect later on, which is Joule-Thomson effect, which is a thermodynamic phenomena, or thermodynamic approach, or thermodynamic concept that we're going to learn later on. Or it can be like heat loss from the gas flowing inside the pipeline. Now, to prevent the hydrate formation from operational point of view, you can do several things. The first approach is to operate outside the hydrate formation temperature. If you still remember the hydrate formation curve, how it looks like, if you still remember, we have this is like the metastable region, for example. If you still remember and we said that anything here you have hydrate formation, anything here no hydrate formation in this region. So from operational point of view is that the first approach in order to reduce the chance for hydrate to form is to operate outside the hydrate formation region, which is normally is going to be like high temperature and low pressure. But this is to keep in mind that this is not always applicable, because sometimes it's not practical to operate at high temperature and low pressure, specifically when you are talking about pumping gas from one station to another station, or if you are talking about even the processing of the gas that we're going to discuss in the next few lectures, that you normally would require high pressure and low temperature. So this is the first approach. The second approach is to do what we call the dehydration, or the drying of the natural gas, where you do the dehydration or the drying is what we call the water removal, where you remove the water content from the gas, or reduce the water content from the gas stream to a point where the dew point should be much lower than the lower expected temperature, and LET stands for the lowest expected temperature, which means that once you remove the water from the gas stream, the dew point that's going to be anticipated at that point, or for the new content of water, which is little, must be much more than, or much less than the lowest expected temperature. So if you assume that your pipeline will experience a pressure or temperature decrease of around, for example, to -20, then you have to assume, or you have to remove amount of water to the point where the dew point should be around -30 or -35, which is less than the minus 20. Okay, and normally dehydration is the ultimate solution because it's always applicable, and that's what we're gonna discuss later on in the once we get to the processing of the gas. And one last approach for the prevention of hydrate formation is what we call the addition of chemicals to reduce the hydrate formation temperature, or what we call the hydrate inhibitors. It's the least attractive option, and why is that? Because from cost point of view first, and then the second point is that you need to add chemicals, you need to inject chemical, which is going to add extra costs from the operational point of view as well. Now for hydrate inhibition, which is one technique to prevent the formation of the hydrate, so you still remember that we have three techniques. The first technique is to operate out of the zone or out of the region where you have a hydrate formation region. The second technique is to do the dehydration, which is well-known approach and well-accepted approach. And the third technique is to do the injection, where you will inject chemicals, and these chemicals will do inhibition or will suppress the formation of the hydrate. And the injection of chemicals is not very attractive in industry for many reasons, such as the cost of the chemicals, because normally the cost of chemicals will be high, which means that you're going to add more cost to the production, and the reliability of the inhibitor injection, how effective is the using of this inhibitors, for example, for this specific gas streams, for example. And third point is the interaction between the inhibitors and other components in the natural gas, such as the solubility, for example, of the inhibitors, for example, in the hydrocarbon phase, and we're going to talk about this later on as well. And the fourth thing is to identify how much is the exact or the proper dosage of this chemical that's going to prevent the hydrate formation and maintain the cost. So which is going to be very hard to optimize, because on one side you need to inject chemicals, and this chemical will cost you money, and on the other side you need to optimize the dosage or how much of this chemical you need to inject, and you want to make sure that this chemical will not interact with other chemicals, or at least it will not be solubilized with other chemicals, or react with other chemicals, or solubilize in other phases, and this will cause like further purification steps that's needed later on once you process the gas. Now, when we talk about chemical inhibitors or chemical hydrate inhibitors, we are talking about typically three terms or three types. The first type is what we call the anti-agglomerates, or the AA. The second one is the kinetic inhibitors, which is the KHI, and the third one is what we call the thermodynamic inhibitors. In terms of thermodynamic inhibitors, we have the old generation and we have the new generation of the thermodynamic inhibitors. The ammonia and the brine are the well-known old technique or old chemicals used to do what we call the hydrate formation inhibition. And the glycol and methanol are the new generation of chemicals that's used to intensively in the industry to prevent the formation of the hydrates. Now, how these how these hydrate inhibitor works, it's different from one type to another type. So if you are talking, for example, about the thermodynamic inhibitors, which is the first type. So the thermodynamic inhibitors, which is glycol and methanol, for example, what they will do, or how the thermodynamic inhibitor function, that it will reduce or lower the hydrate formation temperature, which means that you will get more chance for the gas to flow better without having any or without experiencing any hydrate formation issue. So when we add thermodynamic inhibitors such as salt or brine, for example, or for example methanol or glycol, what you are doing, in fact, you are reducing the hydrate formation temperature, which means that you are giving more time or more chance for the gas to flow without hydrate formation scenario. Now for the second type, which is the kinetic, and from its point, the kinetic inhibitors means that it will reduce the rate of the hydrate formation, which means that the hydrate will form, but it will reduce the rate for the hydrate formation. So instead of the fact that, for example, the hydrate or agglomeration will take place, for example, or plucking of the pipe will take place after 2 or 3 hours, it will take more, for example, 8 to 10 hours for the, for example, for the hydrate to start forming what we call the agglomerate cases, where the agglomerate will contribute to the blocking of the pipe. So this is the kinetic. So the kinetic will reduce the rate of the formation of the hydrate formation. And the last one, which is the anti-agglomerates, where the anti-agglomerates will allow the hydrate to form, but it will not allow the hydrate to agglomerate, which means that the crystal or the hydrate will form, but it will stay as a small crystal, which means that it will not get any chance to agglomerate and cause the blocking of the pipe. And this is what we are referring to, for example. Let me just use green. So if you have no inhibitors, or if you have no inhibition, what will happen with the flow of the gas, for example, this is what we call, or in this case, this is what we call the single crystals of hydrate formation. So if you have no inhibitions added, or if you do not add an inhibition, the agglomeration will keep increasing till the point you get complete block of the pipe, where it's extremely, at this situation we call it agglomerated completely. The system is completely agglomerated, or the crystal is completely agglomerated, and it will cause the blocking of the pipe. Now when you add inhibitors, what will happen? It depends on the type of the inhibitor. If you are talking about kinetic inhibitors, means that the rate of formation will be reduced, means that I will not predict or experience the formation of the hydrate formation early at the early stage, for example, of pumping or the flow of the pipe, of the gas inside the pipe. I will see it maybe later on, or it will take more time for the formation of the gas hydrate. If you are talking about anti-agglomerate, means no, that I will form the hydrate, but the hydrate will stay as small crystals separated from each other, and I will not get to the point where I have complete agglomeration. So this is the different type of hydrate inhibition and how it works. Now, when we talk about thermodynamic inhibitors, as we explained earlier, that the thermodynamic inhibitors, you add the chemicals, and these chemicals will reduce the hydrate formation temperature, or reduce the ice formation temperature. It could be, as we mentioned, it could be from the old generation, which is ammonia and brine, and it could be from the new generation, which is glycol and methanol. But for glycol, the most common one is the EG, or the ethylene glycol, and the diethylene glycol are the most common two types of glycol used for as a thermodynamic inhibitors. For the tri and tetraethylene glycols, they are not really recommended to be used. For the tri and the tetra ethylene glycol, they are not really recommended to be used because of the fact that they are too soluble in liquid hydrocarbon and too viscous. So from one aspect, they are too viscous, which means that it's going to cost you a lot of money to pump them. This is one thing. And then the second aspect, they are highly soluble in the liquid hydrocarbon, means that a huge fraction of these chemicals, or this glycols type, will go with the hydrocarbon, which means that you need to separate again the hydrocarbon, or you need to purify your hydrocarbon stream from these chemicals later on. Now, a few facts about the mechanism of how the thermodynamic inhibition takes place, or how it works. The thermodynamic inhibition. It's well known that if you take, for example, pure water and you try to freeze it, it will freeze at a temperature, for example, 0 degrees Celsius. But if you take certain chemicals, let's say salt, and you dissolve it in the water, for example, it will you will require less temperature to freeze this water, for example, or this type of water. So as a result, it's well-known phenomenon that once you dissolve certain chemical in water, the freezing point, or the freezing or the ice formation temperature will be reduced. And this is similar concept to the idea of what we call the thermodynamic inhibitors. Now, if you dissolve, for example, substances that dissociate into ions, the mole fraction will be based on the ions. Mole fraction for the ion concentration should be used. So for example, if you are using 4.5 mole, let me just change the color. If you are using 4.5 mole percent of methanol, you will get the same depreciation, or the same depression in temperature, similar to using 2.25 mole percent NaCl or 1.5 mole percent of CaCl2. But normally you will not be really using these salt, although they are cheap and can be easily used, these salt, but you cannot use them. Why? The reason is that you will reduce or you will cause what we call the depression and what we call the hydrate formation temperature. It will work fine, but on the other hand, you will destroy you will cause a lot of problems to operation due to the corrosion. Because normally when you introduce, or when you induce salt in your pipeline or in your gas stream, these salts might really contribute to the corrosion issue, which means that you're gonna solve one problem, such as the hydrate formation. You reduce the hydrate formation temperature, but on the other hand, you create another problem, which is the corrosion of the pipes and the equipment as well. And as we explained earlier, that thermodynamic inhibitors mainly include the two things, or the two famous chemicals, methanol and glycols. And when we talk about glycol, so when you inject chemicals, or when you use what we call the thermodynamic inhibitors, such as glycol or methanol, the glycol or methanol will go and bind with the free water that's available in the gas stream. And as we mentioned earlier, the glycols are two types, which is the monoethylene glycol and the diethylene glycol. These are the most common type used in the as thermodynamic inhibitors, in addition to the methanol. But you have to keep in mind that normally, so the phenomena or the concept of using thermodynamic inhibitor is similar to the concept or what we call the in thermodynamic before as the depression and hydrate formation temperature or the freezing temperature due to the addition of certain chemicals. And we gave you the example of water, but we said that we cannot add these salts, for example, in general, because they're going to create what we call the corrosion issue in the operation as well. Now, a few facts to learn or to know about the thermodynamic inhibitor is the fact that if you are dealing with high temperature scenario, then DEG will be most preferable to be used once compared to methanol and monoethylene glycol if you are dealing with high temperature situation. And the second one is that the inhibitors, as we mentioned, will bind with the free water, and then it can be separated as well. And then you can purify this, or you can separate this water. You can conduct what we call the distillation, where you can separate the water away from the, for example, the glycol. But in the case of methanol, it's very hard to do. So for the glycol, you can do the distillation, or the recovery of the glycol from the water stream after you do the injection. But in case of methanol, it's very hard to do, or it's not really economically visible to do the separation. And why is that? Because, as you know, methanol and water are highly mixed with each other, which means that they like each other, which means that it's very hard to separate them through distillation process. You need much more complicated process to separate them. So which means that it's not visible most of the time to separate the methanol from water. So the first fact that DEG is preferable if you are dealing with high temperature. The second fact that the chemical, once you do the chemical injection or the inhibitor using thermodynamic inhibition, you inject the chemical will bind with water. After that, you will separate this water and the chemical with it, and then you can recover part or recover majority of this injected chemical or the chemical inhibitors or the thermodynamic inhibitors. So if you are dealing with a glycol, normally you can recover the glycol using distillation. If you are dealing with methanol, it's very hard to recover the methanol with distillation. Now, if you are dealing with a situation where you need to inject at the wellhead, normally you will use methanol. Because methanol, and as a result, methanol will not be also recovered. And for that reason, it's preferable to be injected rather than glycol, because methanol, when you inject it at the wellhead, methanol will be mixed or will be contaminated with salt water from the formation rocks. Okay, so if you are injecting at the wellhead, if you are injecting the chemical at the wellhead, this means that it's good to inject methanol. And why is that? Because any chemical that you're going to inject at the wellhead will be mixed with the salt that's coming from the rock formation, and as a result it will be very hard to separate that chemicals or recover that chemical. So it's better to use methanol, because methanol anyway will not be recovered. While if you are using injection after the wellhead, means for example after the separator, where you have like a wet gas line or the wet gas line after the separator, then it's recommended to inject glycol, despite the fact that glycol is more expensive than methanol. But the fact that you can recover the glycol is good enough, or justify the fact that you can inject glycol in this scenario. So another fact, that if you're injecting at the wellhead, since the chemical will be mixed with salt coming from the rock formation, then it's better to inject methanol, because methanol will not be recovered. If you are injecting after the separator, let's say through the pipeline, when you have that wet gas stream in the pipeline, if you're injecting in the pipeline, for example, this means that it's preferable to use glycol, although glycol is more expensive than methanol, but you can recover the glycol using distillation. Now, the use of glycol versus the use of methanol. For example, methanol can be used at any temperature. Meanwhile, glycol are used when you have a temperature greater than 15 Fahrenheit or 20 Fahrenheit in some cases, for separation reason. Glycols have certain issue. They are highly viscous, which means that you need more pumping. It will be more difficult to pump them or to inject them. And the other drawback for the glycol is that they are highly soluble in liquid hydrocarbon at low temperature. Therefore, you cannot really use them at low temperature. You need to have at the temperature of around 15 Fahrenheit and more. At temperature greater than 20 Fahrenheit, DEG is preferable to be used once compared to the EG or ethylene glycol. Now, if you look at the depression of hydrate formation temperature, which one will give you the more will be the methanol, which one will give you the less is the DEG, and EG will be in between. Glycol will require you to spray the gas to spray the glycol solution into the wet gas. Dilute glycol, which is mixed with water, will be recovered easily through will be first separated with the water and then recovered through what we call distillation process, which can be done easily, and then once you recover them, it can be reused again for injection. Meanwhile, for methanol, it's very hard because methanol will bind with water, so it's not very easy to separate the methanol with water using distillation. Therefore, it will go straight forward with the stream and go to the dehydration unit, and then it will be recovered with the water in the dehydration unit using the glycol. More facts or more points regarding the comparison between glycol and methanol. For example, glycol will be used when you is cheaper, or will be used, or is preferably used when you have a continuous injection or when you have high gas volumes. Now, on the contrary, or on the opposite side, methanol will be used for when you deal with low gas volumes, or when you deal with a condition where you have a mild hydrate formation condition, or the hydrate formation problem is not really serious. Methanol is always used or betterly used when you have like long lines, since it will give you better protection than the glycols, and the glycols will be also, and in addition to that, the glycols is more expensive than the methanol as well. Now, if you inject methanol before the dehydration unit, there are several operational issues that might arise as well. The first one is the corrosion of steel in the regeneration column. The second one is the co-absorption of methanol and water in the glycol. And the third one is the reduction in the capacity of solid desiccant due to its co-absorption. Now, in terms of cost comparison, for example, the methanol will has, for example, low investment cost because it's cheaper than the glycol, but it has high operating cost. The opposite for the glycol. The glycol have high initial investment cost but has lower operating costs. Glycols will be preferentially used if you have the injection rate for methanol greater than or more than 30 gallons per hour. One other thing, that glycol cannot attack or dissolve the hydrate if it's formed. Methanol can attack or dissolve the hydrate once it forms. Now, if the pipeline is blocked, let's say that you get to the point or to the scenario where you have complete hydrate formation, where you have agglomeration scenario, where you have complete block of the pipe, you can unplug the pipe by reducing or changing the pressure or reducing the pressure on both sides of the plug. But you have to keep in mind that it's very dangerous if you want to reduce the, for example, let me just explain it here, what I'm saying. So that's what I'm saying. I'm saying that you have this scenario. You have the pipe completely plugged at this section, let's say. Okay, so now if you have the scenario of the pipe completely plugged, you can remove or you can unplug the pipe by reducing the pressure at both sides, which means that you're going to reduce the pressure here and here. So here P1 and here P2. So you need somehow to release the pressure at the 2 points, point 1 and point 2. If you release the pressure at 1 point, what will happen? The hydrate might act as a bullet, where it will move directly toward, or might accelerate directly toward the low pressure point, which is really dangerous. It will cause, for example, cracks in the pipes, or it will cause a lot of operational issues. So it's good to reduce, or the practice is to reduce the pressure at the both sides of the block section. If you reduce it at one side, no, what will happen? That the hydrate that's already formed or agglomerated will move directly toward the low pressure section of the pipe that you have already released the pressure at, and will cause the pipe to crack or to break.